안녕하세요, 교수님. Here we present our teamwork on fabrication of piezo-resist pressure sensor using a metal strain gauge with the team member Wang Lei, Raihan, and Bom So. We will introduce our work from this 5 parts. First is overview part to detect the pressure applied to the membrane. A full bridge circuit of the Western bridge was used as a metal sensor. Then we will introduce the more details about the fabrication process, including the membrane formation and the sensor patterning step. It will then move on to present the characteristic system, including the basic test and the amplifier system. And finally, the performance of the sensor will be analyzed based on the data we have collected.
And then we'll continue with the fabrication process. So the fabrication process can be seen in here. There are 16 steps, starting from the wafer preparation and oxidation and the patterning of the PR and the etching, metal deposition, and finally will be the final product assembly. And then the first process of the fabrication will be the membrane formation. So the first one will be the growth of the oxide layer. So we will have the silicon dioxide layer. And we can see in here by this figure, there's a chamber, there's a water reservoir, and also the valve to control of the pure oxygen flowing through the chamber and also the water reservoir. And this process will be done before the PR patterning and also the after TMAH etching. And the purpose is to isolate the silicon wafer with the extra layers, so we are isolating the conductivity of the silicon wafer. And then the process itself, it's the first one we have to prepare our silicon wafer, and we load it into the chamber of the furnace, and then we are setting the parameters where we are utilizing 1000 degrees Celsius of the furnace with the time of the heating of 40 minutes because we want to achieve target thickness of 300 nanometers. And this degree Celsius, this temperature, it's to have chemical activation of the water vapor and also silicon wafer. Because if you can see in here, the pure energy, the pure oxygen will be linked with the water vapor at the surface of the silicon wafer at such temperature. And then the second one is the photolithography, and we want to achieve the mask to TMH etching for the next step. And then the process itself, it's a spin coating, pre-exposure bake, exposure, post-exposure bake, and also the development. And we will do the exposure of this wafer in the MEMS and NEMS technology laboratory in National University. So the fabrication process for the photolithography, the first one is to prepare the SiO2 that already we prepared before, and we will be utilizing the dried and also the wet cleaning to remove the moist and also the dust, and heating also for sometimes at 120 degrees Celsius. And the second one will be the spin coating to achieve desired thickness by 1.5 micron thickness, and we can achieve it by the 2000 RPM for 30 seconds. And then we will soft bake it 90 degrees Celsius for 90 seconds. And then the fourth one will be the edge bit removal, so the contact will for the photomask and also the photoresist will be sufficient, so there will be no air gap between. Another one is the exposure by the light intensity of 90 millijoule per centimeter square. And the sixth one will be the post-exposure bake by the 110 degrees Celsius for 90 seconds. And last one, it will be the development. And for this node, we are utilizing the positive photoresist of AZKXR601. And then the third one will be the edge. So the purpose of this one, we want to trench, or we want to achieve a depth formation of the silicon wafer. And the first one will be the HF etching. So this step is to remove the silicon oxide a layer on the surface. And the second one will be the TMH etching to achieve the desired depth. And then the first one, uh, the the first one will be the HF etching. So we will prepare our silicon dioxide layer, and then we will make a solution of HF by the 40% of HF in the DA water. So the etching rate will be 75 nanometer per minute, and we will pat it for 4 minutes, and then we will rinse it for 1 minute in the DA water. And then to remove the excess water and also the HF, we will use a blower gun. And then the second one will be the acetone bath, and this is to remove the remaining PR because the PR is to have a pattern on the silicon dioxide layer, and we already remove the pattern of the silicon dioxide layer, and also we have to remove the photoresist. And then the last one will be the TMAH etching, and we want to achieve 50 microns of depth. And then the step is the first one will be the silicon wafer preparation, and the second one is to have a solution by the TMAH 25% weight total in the water. And then the third one is to bath the silicon wafer into that TMAH solution. And then we will heat up by the hot plate around 80 degrees Celsius about 1 hour and 40 minutes. And to have information for the etching, for this concentration, the etching rate it's around 0.5 micrometers per minute. And after that, after it finished, we will rinse it with the DA water for 1 minute and also remove the excess water by the blower gun.
After the membrane formation and insulating layer deposition, the metal deposition and sensor patterning will be conducted to measure the pressure with the metal strain gauge. The metal strain gauge measures the pressure with changing resistance as the membrane deforms. The metal deposition will be processed by sputtering to make the full Western bridge circuit. After that, we will make the circuit pattern by the photolithography and etching process to make the sensor on the substrate. The first step to make the sensor pattern is metal deposition. We will use chrome metal and sputter for the metal deposition. The sputter machine, as shown on the left-hand side, is the equipment that we are going to use in the MEMS lab and shows the main parts of each section. For the sputtering process, we first prepare the cleaned wafer, which we previously etched and coated with the insulating layer. The sputter machine setup starts with the chiller set for ambient working temperature and high vacuum state setting. As the sputtering requires a high vacuum working environment, we need to make sure that the required vacuum conditions are achieved for each chamber. To load the substrate in the load lock chamber, we will inject the nitrogen to release the vacuum condition. The substrate will be placed on the loading arm. For the high quality of metal deposition without uniform metal deposition, we should make sure there is no other dust between the load arm and substrate, and clean the device surroundings for perfect chamber sealing. Next, the loaded substrate will be transferred to the main chamber for the metal deposition. Then, for the deposition preparation, we will connect the power cable to the target metal chamber and make sure the secure closing, and set the argon flow rate and control the air pressure within the main chamber. The pressure affects the quality of the deposition, so we use the usual set for 0.002 millimeter per Hg. Last step of sputtering is control of output power. The output power is directly related to the quality and rates of metal deposition. The higher output power induces fast deposition process with low quality. So we need to carefully control the output power, and we decided to use the lowest output power of 50 watts for high quality deposition. After the power setting, we can start the sputter process and finish the metal deposition after enough deposition time. After the metal deposition process, we will make the sensor pattern by photolithography and etching process. First, we will coat the metal deposited substrate with the PR for photolithography, and then expose the UV light with the patterned mask for curing the PR. We can develop the UV exposed positive PR and etch the unwanted metal leaving behind the strain gauge pattern. The last step is the backside etching to make the bridge. We can cut both sides of the substrate with PR as protecting layer for the top side and the patterned side for backside. And we will etch the bottom side of the wafer and then make the bridge with removing the PR pattern. The depth of the etching should be carefully controlled considering the open window pattern on the top side to make sure it is not broken. The sensor will be packed with the housing for the experimental platform. To test the sensor device, we will induce air pressure on the bottom side with the syringe or pressure pump. To do so, we will make the housing which attached at the bottom side of the sensor and where the air can be injected without leakage. We will use high-resolution 3D printer for the leakage-free and smooth surface of the housing. The printing process will be in 3 steps: modeling, printing, and post-processing. The last post-processing will be carefully dealt with for the smooth surface by washing and post-curing. The housing will be attached to the sensor with UV epoxy to prevent air leakage.
Once the fabrication process is complete and the final device is ready, a series of basic tests will be conducted to test the performance of the device. For the basic test system, the cylinder pump will be used to increase the pressure inside the cavity, with the reference pressure sensor providing a reference pressure value. As the pressure changes, the output voltage of the device will also change. However, due to the low output voltage generated by piezo-resist pressure sensor, an amplifier will be necessary to amplify the signal. HX711 is selected as amplifier for its simple setting and usage. The output signal from the sensor will be amplified by HX711, and the amplifier signals will be sent to the Arduino mode, which connected with the Wi-Fi mode. This system amplifies the signal and transmits the data via the wireless model. We find out the optical image of HX711 amplifier and its pin description. And since the amplifier is connected with sensor and Arduino, so the wire connection schematic is also showed. To more accurately define the connection, we also find the wire connection method is also shown in the table. So in this one, we can make sure the connection between sensor, amplifier, and Arduino is well. The details of Wi-Fi module is shown in this page. Since the Wi-Fi module is only connected with Arduino, we find the connection method between them. Here we also show the optical image and the pin description of ESP8266 Wi-Fi module. And also we have already defined the wire connection method between this Wi-Fi module and the Arduino module. For the program part, this is one of the difficult things, and right now it's still starting, and we will further improve it in the future. And here is our schedule of the team project, including the fabrication and to the final report preparation. Finally is the individual contribution during the technical discussion. The responsibility part of each member is shown below. That's all. Thank you, Professor.